All right. Welcome, everyone. So sorry for the delay today, but everything went smoothly, and so we can wrap up our discussion of the Kondo lattice and maybe start the next topic. So the Kondo lattice is pictured here. You have conduction electrons, which are highly mobile and essentially free, that are moving in one band. And then you have another band of electrons, which are essentially stationary, and we call them the F-electrons. And they are spins that are sitting then, therefore, on these F sides, spin a half in our discussion. And these spins interact via the exchange coupling, JK, to the conduction electron. And what we are also doing now in order to complete our treatment is also put in what's called the Heisenberg coupling between the spins themselves. So thinking very naively, you can imagine two situations now. One in which the spins form singlets with the conduction electrons. That's the usual Kondo effect. But we can imagine another such situation where the spins form singlets with each other. And they form what's called a spin liquid state. So we're going to talk about that state today. I'm just going to do the very basics of spin liquid theory. It was something covered in much more depth, at least for insulators, in the previous semester. And well, you can watch the lectures online. And to leading order anyway, the spin liquid that appears on the F sides is not so different from the one that you get in the insulator. Anyway, before I proceed, any questions then on that introduction? Is there something on chat? Okay, you can hear me, right? Yes, go ahead.
So is the spin liquid also there for 1D case on the F sites? Or does it need to be like higher dimensions?
Yeah, that's a good question. So 1D is a little tricky because there's no concept of topological order. And even there's no concept of a Fermi liquid. So there is, however, still as an analog of the Luttinger theorem, which relates the density of all the electrons and spins to where there are singularities in momentum space of the correlation functions of the various particles. And that Luttinger theorem, which was, I think, proved by Oshikawa and Affleck, is always obeyed. So you never get a violation of the conventional Luttinger theorem. So, however, in 1D, you can imagine situations where you have two separate Fermi surfaces, one for the F electrons and one for the C electrons. So there is an analog of the FL star phase, but strictly speaking, no. So in 1D, strictly speaking, the Luttinger theorem is always obeyed, or the generalization thereof. So you have to be in 2D or higher. Good point.
I see, thanks.
Yeah. Any other questions? All right, so we proceed by the Hartree-Fock method, as always. That's really the one trick we have learned, and we are applying it essentially in every topic. I think the SYK model will be the first place where we will have a new trick. Okay, the trick is whenever you have a full Fermi operator, you factorize into products of two Fermi operators. So in this case, you get Kondo coupling, which you factorize into products of the QI, which is this expectation value of C dagger F. And we showed that for the Kondo problem, it led to a very successful description, which was confirmed by other methods. And now you also factorize the Heisenberg exchange in an exactly the same manner into F dagger I, Fj. So now this is sitting on the links. All right. So I discussed a little bit about the gates symmetry and the gate structure. We'll come back to that. Let's just go ahead and first look at the equations that are satisfied by the QI and the Pij. Okay, so you do this factorization, We'll come back to the gauge symmetry. I've already talked about it somewhat. And you get the Kondo-Heisenberg model. And this looks almost exactly the same for the Kondo model, with a few small differences, of course. For the Kondo lattice model, since momentum is conserved, the Q terms with that mix the F and the C don't have any sum over momenta. There's only a single momentum. They just conserve momentum. So that was as for without the Heisenberg coupling. And the new thing is now this. There's now a dispersion of the F dagger. And where does that come from? Well, that comes from you had a term, you have sum over, let me rewrite the term a little differently. You'll get sum over I and sum over vectors to the nearest neighbors. So you will get some terms like P, I plus E. What is that label? E sub A, where A, so if here's a site I, then this is the vector E1, this is the vector E2, this is the vector E3, and this is the vector E4. So for a square lattice, you have 4 neighbors, but in general, you have Z neighbors, or Z is the coordination number. So you'll get something like this times F dagger I alpha times F I plus E alpha. And now when you do a Fourier transform, this becomes sum on K, PK times F dagger K alpha, Fk alpha. It preserves the momentum times PK, and PK is sum on EA of E to the I. Okay, so we're going to now assume that these P's are all uniform, the same on every site, and that that uniform value is just P, and E to the I K dot E alpha for uniform. So even if the P's are just constants for same value on every link, you will get some K dependence just coming from the fact that the site index on these F's is not the same. So you get some dispersion for the F spin-ons, as we call them. Okay, now this is of course a highly simplified assumption. When you really try to do a series theory for the spin liquid, there's a lot of freedom here in how you choose the P's and how they transform under gauge symmetries. And that's really a whole subject with all kinds of different types of spin liquids you can get, which we're just going to ignore here. You can get U1, Z2 spin liquids. You can even get spin liquids with non-abelian statistics and all of that. All of that is possible, but we just take the very simplest case where these P's are uniform, and basically the F's are just spin-ons. The spin-ons are just fermions moving in some dispersion. Okay. So that's the P bar. That's the P bar value, which is the uniform everywhere. And this is this factor that I told you about. Okay, so that's the Hamiltonian. And finally, we have to find what is P bar. So there's a self-consistency condition for P bar. And P bar is just expectation value of F dagger F. And you just go through the same procedure I had before, and you keep track of all the factors, and you can find P bar is related to the expectation value of F dagger F. And the equation for Q bar is the same as before. And F lambda bar, we obtained that in the previous section. Just to remind you, the equation for Q bar is way back here. Yeah, here. So these equations remain exactly the same. Q bar is JK times C dagger F, and lambda just to determine the density. Okay, so what we found earlier, that this equation was really the key. And we showed that you always had a solution with Q bar not equal to 0. There will be actually one more homework, and in the content of that homework will be lead you through a calculation where you show that this solution with Q bar not equal to 0 is the lowest energy solution. So you will actually compute the free energy. And okay, I'll guide you through that for the last homework. All right, so now we just have to look at the form of this this object. And so this is just the expectation value of C dagger F. So for that, I need the Green's function for GFC, where the Green's function, remember, we just obtained by summing all these graphs. Okay, so GFC, then I can write it out here. GFC is something like, what is it? F propagator is a dashed line, then a straight line, then a dashed line, and that's it, and plus dot, dot, dot. So you'll get, it starts with an F and ends with a C. Okay, and no, let me not put an X over there. And each factor of X is a factor of Q. So if you sum these series, what you'll find, let's write it over here, GFC will be something like, well, let's see, we had an expression here, so let me just recall that one. Let's just take this expression. Yeah, here it is. The GFC is Q bar, which is GFF, the bare GFF, times GCC. But now this has a dispersion, which is EK. So what you find is that GFC is minus the F propagator, EFK, times the G, it goes from F to F, and then F to C, sorry, yeah, and then CC. So that'll be I omega N minus EK without the F, minus mod Q squared over I omega N minus EFK, and then there's a factor of Q bar somewhere. Okay, well, this is just, this is easy to simplify, and so you just expand that out, take this product in this factor in there, and you get what's in the notes then. So finally, you get this expression here. Yeah, here. So I've already skipped another step. So the original expression is Q bar over J equals Q bar over V, sum on K, or 1 over I omega N minus EK times I omega N minus EF of K minus mod Q squared. Okay, so now you have to evaluate these summations. And the quickest way to evaluate the summation is to just look at the poles of the expression. But the poles of this denominator are precisely the eigenvalues of the two-band Hamiltonian that we wrote down last time. The only difference is now you just replace the lambda bar by EFK, which depends on K. Okay. And so then when you evaluate the summation, this just becomes, in fact, this term originally was something like, this was originally something like F of EK plus minus F of EK minus over EK plus minus EK minus. Okay, so that's the full expression at general Q. And what I've done here is taken the Q goes to 0 limit. I don't cancel this out, but I can evaluate this at Q equals 0. And basically what happens at Q equals 0, that these two band eigenvalues if you have this band, you have a F band and then you have a C band, and then they mix to give you these two bands. So the initial summation here is over the blue the orange lines, but as Q bar goes to 0, it becomes over the blue lines. And then it's really convenient to just rearrange the sum over K, where you always call this one band and that the other band. And so it's just the Lindhardt function between the F band and the K band. Okay. And now the point is that this thing is finite. As Q bar goes to 0, this is finite. This is because this is just like Lindhardt susceptibility, which we know is finite at finite Q. So you have two different band structure, unless something peculiar is going on. These band structures are not identical, and this is just some number. And because it's finite, it means that as J, this would be J sub H, I think. Sorry, did I call it J sub H? No, I just called it J. Excuse me. Yeah, it's been J consistently. I didn't call it J sub H. Okay, so as J goes to 0, so for very small coupling, but this should be JK. That's a mistake. This is JK. I'll fix that. Because we are really looking at the value of Q bar, not the value of P bar. So as JK goes to 0, then the left-hand side has its Q bar with a coefficient that blows up, whereas the right-hand side, Q bar times some number. So for small enough JK, if the coupling to the conduction band is weak enough, Q bar must be 0. That's the only solution. And therefore, voila, we are now at the situation I claimed we were at last time, where this is just JK, this Q is just 0, and there is no Kondo effect. So now we have a situation where the conduction electrons moving on their own and form a small Fermi surface, and the spins here are forming a spin liquid. And this spin liquid necessarily, because of the gauge structure that we discussed, has an analog of a photon. It has an emergent photon. Here, for this is the simplest U1 case, where the photon, has the Maxwell action. There are more complicated flavors of spin liquids, which would take me too far afield to discuss here. But I guess the point I want to emphasize is that if you then look at the structure of the Luttinger theorem, how is it that you're able to satisfy the Luttinger argument? There's a Luttinger argument, what fails with it? And you find is that if there is an emergent gauge structure and you're in this deconfined phase as far as the photon is concerned, then you can get a modified Luttinger theorem where you only count the Fermi surface only counts the volume of the conduction electrons, not the F-electrons. And there's no such state in 1D. This is can only possible in 2 and higher dimension, strictly speaking. Okay.
Subir, I had a question here.
Yeah.
So you said if JK is very, very small, then you get a spin liquid in the F electrons. But is this any different from not having the conduction band at all and just having just fixed spins on the lattice?
It's not really. I mean, ultimately, it's not. And there are also various theorems for spins on a lattice. If they form a spin liquid, that there has to be an emergent gauge field. Otherwise, you run into some other theorems, I guess sometimes called the Leib-Schultz-Mattis theorem, the Hastings-Oshikawa arguments, and so on. These are all different versions of basically the same arguments. And in this context, it's the Luttinger theorem that gets modified because of the presence of the emergent gauge field. But I think the idea is that ultimately the there is a JK in the real system, and it's only in mean field theory when you're in the Higgs phase where this Q bar is 0. But there are fluctuations of Q, which means that the interaction between the spins is influenced by the presence of the conduction band. It's not as if it's not there. And in particular, there's something called the RKKY coupling, which is kind of long range. And so the spins have a long range coupling between them due to the presence of conduction electrons. So it's only zero in mean field. There are lots of corrections, but all of those corrections, one can show, don't modify the Luttinger argument because of this existence of this Luttinger Ward functional, ultimately. But yeah, so, in the end, it seems like a totally obvious statement, but it is quite subtle. And in practice, in the real world, the hope is that because you have this coupling to the conduction band, and these couplings are so frustrated as a result, these J sub H, they get modified by the presence of the JK. And that leads to sufficient frustration that the Fs will form a spin liquid. So in a real system, it could be that if you just remove the C, the Fs would form a magnetically ordered state. But if you bring the C in, they don't disturb it very much, but they disturb it just enough to get rid of the magnetic order and they form a spin liquid. So in that sense, having the C around is important because it allows you to access a regime of parameter space that the Fs wouldn't access on their own.
I see. And actually, I wanted to ask about the frustration. So you mentioned that with the C, it gets frustrated, but if it's on like, say, square lattice, then is there still frustration? Or
yes, because so the coupling between the Fs is oscillatory. It oscillates. It's very much like the Friedel oscillations that we learned about. So there's a version of the Friedel oscillations in the effective coupling of the F spins, and that also oscillates at the 2kF wave vector. So the couplings that you induce, the C electrons induce on the F spins, has both signs. So there is some frustration on any lattice. It's just a question: is it large enough? So so you want to make JK fairly large so that it induces some frustrated couplings here, but you don't make it so small, so large that you just get a heavy Fermi liquid. Then you go into the other state. So there's a delicate balance there.
Okay, thanks.
Any other questions? So that concludes this chapter, which has really gone on quite long, on the Kondo effect and the Kondo lattice and the heavy Fermi liquid state, and this more exotic FL star state, which is very much a topic of current research, and there are now at least a couple of fairly convincing sightings of it in experiments. Okay, well then we have another 20 minutes. So I'm going to start the next chapter. So this is kind of a chapter on disordered metals. Okay, so we're, at least for today, just consider free electrons. But now moving in some lattice with some impurities. Of course, this is absolutely crucial to understand real metals. There's always impurities in metals. And what is the effect of the impurities on various properties of a Fermi liquid? The short answer is that not very much. The impurities, when they are weak, they change the one electron eigenstates. Instead of the eigenstates being plane waves, they become almost like plane waves, which undergo phase shifts every time you encounter an impurity. So you have some kind of wave function, which is oscillating, then undergoes a phase shift, and then undergoes another phase shift, the next impurity, and so on. So there's some kind of random phase the electron picks up from the impurities. But it's very important to keep in mind that this random phase is not the same thing as decoherence. And this is what led to lots of interesting effect. It's not decoherence because the phase is fixed. That is, if another electron came by and went the same path, it would acquire the same phase. It's because the impurity is static and sitting there. Decoherence requires, dephasing between the phases of the different electrons so that quantum interference effects disappear. Okay, so that's all right. So an important thing to keep in mind, and that's what leads to a lot of interesting phenomena like universal conductance fluctuations, which I'm not going to be discussing, but I'll at least introduce some of the effects of this interference. Right. So if I have a disordered metal with these dephased eigenstates, it'll have some density of states at the Fermi level. As you've seen, when we're looking at properties of the Fermi liquid, that's one of the most important quantities. It leads to determine the specific heat and the compressibility, instability to ferromagnetism, instability to the Kondo effect. Everywhere we just saw the density of states at the Fermi level. And this is not a quantity that's changed very much by the presence of impurities. So to zeroth order, there's not much change to everything you have learned when you have some impurities in a metal. Of course, if you have the impurities carry spins and you have an interaction, that's of course a different ballgame, and we just talked about the Kondo effect. However, there's one property that really is determined by impurities, and that's the conductivity, at least for a big enough metal. And that's what I want to describe, at least show you a computation of how the conductivity proceeds. Because if you have a perfect lattice, then the conductivity is just infinite. It's not quite a superconductor because a superconductor, the conductivity remains infinite even after you put in impurities. But here, the impurities lead to a finite conductivity, and that's the famous Drude formula, which we're going to describe for the case of coherent transport, no dephasing, coherent transport of electrons in the presence of impurities. So when you do that for a dilute collection of impurities, you reproduce the Drude formula. And the Drude formula is essentially classical physics. It's got nothing to do with quantum interference. It's just particles undergoing random walks, and you just average over them. Somewhat surprisingly, and maybe a bit disappointingly, even when you do the same calculation for coherent scattering of waves of impurities, not just particles undergoing random walks. If you just take waves undergoing coherent scattering of impurities, you find in the end that you get the same Drude formula. But that hides a lot of interesting, that hides the difference. Even though it's the same formula, the actual mechanism of that determines the scattering time and determines what's going on in a metal at low temperatures is a very quantum phenomenon, and it's very, very different. For example, if you were looking at the conductivity of some ions in a solution, you put a voltage in a solution and you've had the ions moving around very classically, and you got some conductivity there. That's a totally different physical situation, but as I said, somewhat disappointingly for the conductivity anyway, you get the same answer. But it's a bit of an accident, I believe. However, there are other things you can look at other than the conductivity, like the Hall effect, for example, or the temperature depends on the conductivity, and or the fluctuations of the conductivity, where you see huge differences from classical transport and quantum coherent transport. And one of the first places where people started recognizing that there's something coherent about transport of electrons in metals is what's called the weak localization effect. And I'll talk a little bit about that. And I think one of you, I've forgotten who, will be making a more presentation in more detail, but I'll kind of just introduce the topic of weak localization. And weak localization is where the conductivity gets reduced because of quantum interference effects between the different waves scattering of the same set of impurities. Okay, so with that preamble. So we're just going to take this very simple model. You have conduction of electrons. I've even ignoring spin here with some well-defined dispersion E of K, and they scatter off some impurity potential V of R. Okay, and this is some finite density. There's a chemical potential which has been put in here. Okay, and as written here, this is treated at some length and quite a lot of complexity in Bruce and Flensburg. Some of it is a bit unnecessary, but it's very thorough and nicely done. Okay. All right, so this is our impurity potential, and we are going to now, so far when we did the resonant level model or the Kondo model, this was this was only on one site that there was an impurity, but now that impurity is scattered everywhere, and so V of R, we just assume is some random function of R. So this is R. Okay, and it's weak. So we want to statistically answer some things about the Green's function properties. So what we're going to compute first is the average Green's function, and in the presence of some potential over some ensemble of V of R. But the hope is that the ensemble average is the same as the self average. And if you have a big enough sample, then different regions of the sample have different V of R's, and the electron is extended, it's going through the entire sample. And as it visits all the different parts of the sample, it effectively does an average over V of R. So perhaps just computing the average Green's function over an ensemble of V of R is the same as computing the actual Green's function for a given electron in a given sample. That's kind of the assumption in this whole averaging procedure. Of course, that may not be correct. There may be some observables where, in fact, the ensemble average is not the same as a self average in a given sample. So the way you can test for that is by measuring moments of, take the second moment and the third moment, measure the variance and so on. That's pretty much what you do. For what we're going to compute here, the ensemble average and the self average are pretty much the same thing. But there are, I've already mentioned universal conductance fluctuations where there are important fluctuations in mesoscopic samples where there's very little dephasing due to electron-electron interactions. And that's a whole subject. There's I think a little bit about it in Bruce and Flensburg. And if some of you are still looking for or want to switch your topic, would be a very nice topic for your presentation. Okay, but so far no one's chosen it, it seems. All right, so we take an ensemble of V of R, and we'll take an ensemble where the V has 0 average value. That's not much of a specialization because you can always take the average value of V and put it inside epsilon of K, so it doesn't matter. And then it's called as some second moment. V of R is some second moment, V naught squared. But we'll put a delta function here saying that the V of R at this point has nothing to do with the V of R at that point. They're just totally uncorrelated. The impurities are at random positions. Just because there's an impurity here, it doesn't tell us anything about whether there's an impurity on the next site. They just go randomly on different sites. That's the idea. And so that in the continuum limit gives you this delta function. Of course, you can make this a finite range, some finite correlation length. It won't change very much to anything we talk about. So this is a very simple limit to study. Okay, so now we want to do this ensemble average over different impurity configurations and compute the Green's function. Okay, so the bare Green's function is just that, of course. And now we're going to put in this as an interaction. And the set of all graphs is really very simple. Let's do it in momentum space directly. That seems what I've done. Take the Fourier transform of V. You're given some fixed V, take a Fourier transform. Then you have the bare Green's function, then you have one interaction. You get a factor of V for that, and the momentum will change. And then At next order, you'll get two of them, G naught, G naught, G naught at three different momenta, and the V's at the momentum transfer. Okay, and so on. I mean, that's the entire, the exact answer for any given V of K. You just get the geometric series. You get G naught V, G naught, G naught V, G naught V, G naught, and so on. Okay, so you have an infinite set of terms. And now we're going to do, and we've met these terms already for the Kondo problem. What we're going to do is average every one of them. So you're going to average, and average is usually denoted by an overline. So the average means what's called, sometimes called a quenched average. It's not a quantum mechanical average over wave functions. It's an ensemble average over different Hamiltonians. You have a whole set of Hamiltonians, H, infinite set. For each Hamiltonian, you get the exact Green's function. And then you average the Green's function over the ensemble of Hamiltonians. Seems like a horrible thing to do. That's because in a real system, you're never doing that. In any lab experiment, you're never doing an ensemble average. But we're going to do it, and it's actually extremely successful for many things, including the Green's function. Anyway, so we ensemble average each term with this rule. So this rule tells us, you can write this in K-space also. You just take the Fourier transform of the left and the right-hand side. So I think in K-space, you're going to get something like average of V of K is just, of course, 0. An average of V of K prime, average, and it'll be V naught squared. And I'm thinking it should be delta of K plus K prime, but something like that. When you take the Fourier transform off the top of my head. Basically, what it does is just pairs two V of V's together. All right. So when we do this here, from this term, we see that this is just 0. So if I take an average of this term, average of this term gives me 0. All right. What about this term? I take an average of this term. Now I have two V's, and I'm going to get something. And basically, the average of this, the way we write it, is equal to since you're averaging these two, you bring them together. This V naught squared. And now you just think of this as some line that can carry an arbitrary amount of momentum. So this was K. This is K prime. And now total momentum should be conserved after you do the average. So the momentum, K minus K prime is a momentum that flows there and comes back out. So if momentum is conserved through this line, then this thing is going to be K again. It's not K prime anymore, it's K. And this delta K plus K prime here has made sure that happens. And it's not surprising, momentum should be conserved once you average, because once you average, the system is translationally invariant again. So the Green's function actually becomes diagonal momentum. So on average, if you send in the Green's function here with some momentum, electron with some momentum K, it'll come out with the same momentum K on average. Of course, it could have other momenta, but the amplitude at the other momenta averages to 0 and could be very small for a huge system. Okay, so the second order term is just this. So it's G naught squared. That's this this term here. Sorry. There's this term here and that term here. That gives you a G naught squared. And there's the V naught squared that comes from this X where you have, and then there's a G in the center, which you have to sum over K prime or K double prime. Okay. Okay, so that's the second order term. Let me just write down the next order term and see what we get. Just draw some pictures. So this can all be done with pictures, and that's really one of the power of the Feynman graph expansion. Okay, so at third order, we can see without any trouble, at third order, the average has to be 0, because when you have an odd number of V, then because the mean is 0, and we also, okay. The other thing we're assuming is these are Gaussian random variables. And what that means is that you can, you have something like Wick's theorem, which means that if you have the average of 4 variables, it just factorizes into average of pairs of variables, and so on. So the next term that we're going to find that's non-zero is with 4V. So you have 1V here. Okay, and now you're going to average this object. You're going to average the whole thing. And the content of saying these are Gaussian random variables is that you take these points and you start pairing them. So this average is equal to, you'll see that there are 2 possibilities. Well, actually 3. You can get something like this. Yeah, so you can get something like this. Okay. And so when we look at these graphs, just drawing pictures, it seems that we can give a simple interpretation of this. This particular line, is electron going around. It scatters off some impurity, it moves back, and then it scatters off some other impurity. And basically, these are independent scattering events. So this kind of term we have, we know how to take care of. We just put this scattering event in the self energy. Just put it in the denominator and you sum all the whole thing. This also seems like a reasonable thing. Here, the electron is scattering off some impurity, but in the intermediate state, it scatters off another one, but then it comes back to the original state and scatters off the first one. And this is also something we can take into account simply by putting in the full Green's function here rather than the bare Green's function. And this, it turns out, yeah, all of this, the first 2 terms we can take into account quite easily by the tricks we have learned of the self energy and going from bare to full Green's functions. So they're basically essentially summing over each scattering event in a classical manner. You're just summing the probability for each scattering and just putting that into the average Green's function. And it's these are essentially classical type effects. And it's because these are essentially classical, because each impurity scattering is uncorrelated with any other one. This is why in Drude theory, the end theory ends up looking classical. But this is the first one that's a little more not trivial. This is a quantum interference effect. Here, somehow the scattering of one impurity is interfering the scattering of another one. If you try to give some space-time interpretation to this particular graph. So this is the most interesting graph, which can lead to corrections. So I'll just put an exclamation part here. But it turns out you can argue that at least for small impurity density, these terms are weaker and you throw them out. So that's a somewhat subtle argument. In fact, the argument is not quite correct. And misses all the quantum interference effects, which lead to all kinds of interesting phenomena. But if you're, our purpose first is just get the Drude theory, the analog of Drude theory for quantum particles correct. And that comes from, actually including just these and throwing out the other one. And that's what we'll do first on next lecture. Okay. Any questions? And I can also put the momenta in if you want to see how this works. So this is momenta k, this is k prime, that has to be k again. This is k double prime, and that has to be k again for momentum to be conserved. And this has to be k, this is k prime, that has to be k double prime. And now for momentum to be conserved at this object, it has to be k prime again, and that's k. So not anything interesting. But now here, life becomes more complicated. This is k, this is k prime, and now this is some other k double prime. And now here you have to conserve momentum from this vertex and that vertex going this way. So this has to be this k double prime coming in from here, and there's k minus k prime coming in from the dashed line. So that'll be plus k minus k prime, and then it's that better be k again. So that's why I said there's some quantum interference. There's something that depends on the actual momenta of the intermediate states, and there's some indifferences, and so this graph is more complicated to evaluate, and it leads to interesting wave-like interference effects that you wouldn't find for a classical particle. Okay, so no further questions, then we'll stop there and have a great weekend. I think the problem set is due today, and I'll try to put the new problem set online by Monday. And there will be a discussion session tomorrow at 9 a.m. Okay.